factoring special cases is where we take those shortcuts that we found earlier in the chapter, and it makes factoring much easier because if you can spot how they are special, then it is much easier to factor them. So our learning target is that we can factor the difference of two squares. So first let's look at a perfect square trinomial. If you'll remember, whenever we looked at this earlier in the chapter, the first term was the square of the first term. The second term was 2 times twice the product of the first and last terms. So it was 2 times x plus y. And then the last term is the square of the last term. So factored out, it would look like this, x plus y squared. So that's all good and fine, but what you need to know is how to spot a perfect square trinomial. When you're looking at these problems, if you see that the first and the last terms are perfect squares, if you see x squared, and then on the end you see something like 4, 9, 16, 25, 36, 49, and so forth. If you see perfect squares, then your brain should start to have a flag that comes up and says, ooh, that last term is a perfect square, so would it work if the middle term was 2 times the product of the two terms? So if this was a 49 here, is this middle term 14x? Because it would be 2 times 7x. So let's practice this a little bit. Keeping in mind our markers that the first and the last terms are perfect squares and that the middle term is 2 times the product of the two terms. So how I usually spot these is I notice, hey, there is a perfect square on the end. So I write it out and I say, let's say that it was x plus 3 squared. Would that work? Is it 2 times 3 times x? 2 times the x and the 3, and that does give me that middle term of 6x. So see how that was a lot quicker than factoring. If you had done it the other way with the columns, what you would have done is you would have had the factors of 9, which would have been 1 and 9, and that would have added to be 10. And then you would have said, okay, the other way I could do that is 3 times 3. 3 times 3 does add to be 6. Okay, so there are my terms, and I would have x plus 3 times x plus 3. And then hopefully you would have noticed that those are the same and that you could just write it squared like that. You could still do the columns, but as you can see, it's a lot quicker if you can spot those perfect squares. Let's go to this next one. Notice I have a negative middle term. So what are the square roots of 49? Well, it's 7, but it could also be negative 7. Since I have a negative here, that means that I'm going to have x minus 7 squared. Again, I could have done my columns. I could have done 49 and 1. So that would have been negative 49 and negative 1 in columns, which would have added to be negative 50, not negative 14. Well, then the only other factors of 49 are negative 7 and negative 7. I'm ignoring the positive because I know they have to add to be negatives. So negative 7 plus negative 7 is negative 14. Again, you can do the columns. However, it's much quicker to spot those perfect square trinomials and then just go directly to the factored versions right here. So the other type of special case that we looked at was a difference of two squares where you had a squared minus b squared. We presented it earlier in the chapter where you were looking at this side of it. A minus b times a plus b. When you foiled that out, the middle terms canceled out because you would have a negative ab plus ab. So what you're left with is a squared minus b squared. How do you spot a difference of two squares? There is no middle term. There's no b term. Only two perfect squares on either side. And there's subtraction between those two terms. So this might look like a squared minus 25. That would be a difference of two squares. There's no middle term, and they're both perfect squares. The square root of x squared is x. The square root of 25 is 5. It has to be the subtraction sign there in order for them to cancel out, so that would expound out factored to be x plus 5 times x minus 5. So this would be the factored version of that difference of two squares. Let's practice this. So we have our hints here of how to spot this. There's no b term here, only two perfect squares. So that is going to be v plus 10 times v minus 10. They have to be different size because it's a difference of two squares. 10 times negative 10 is negative 100. If I would have had two positive 10s, my C term would be positive 100, and I would have v squared plus 20v plus 100. Nothing would have canceled out. Likewise, if I would have had two negatives, I would have had negative 20v as a middle term, and then a positive 100. Here, I have two perfect squares. I have x, and I have negative 16. So that's going to be x plus 4 because 4 is the square root of 16, and x minus 4. Now, sometimes they get a little bit more complicated. When you look at that initially, you aren't seeing any perfect squares. So sometimes you have to factor out a common factor first. So I look at those two terms. I look at the numbers of them, and they have a 12 in common. So I can factor out 12. So I'm left with t squared minus 4. Now what I'm left with is a difference of two squares. So I'm going to leave the 12 there, but then I'm going to bust up t squared minus 4 into its square roots, t plus 2 and t minus 2. One is adding, one is subtracting because it's a special case of a difference of two squares. That way the middle term cancels out. And there would be my factored form. Likewise on this bottom one, 12w squared plus 12x plus 3. I have a common factor of 3, so I can pull that out. 3 times 4w squared plus, well, here, that right there, I made a typo when I was making this. There shouldn't be two different variables in there. That should be a 12w. Okay, much better. So if I pull out a 3 of 12w, I'm left with 4w, and 3 divided by 3 is 1. Okay, now what I'm spotting here is I am seeing a perfect square trinomial. So the perfect square is the 1 right here. So if I did a 2w here and a 2w here, that is going to give me the 4w squared because I multiply the first terms there. Now what is the square root of 1? Well, it's 1. So I'm going to have plus 1 and plus 1. Now this one is probably as most complex as you're going to see. Let's foil it in our head so that we understand what's going on here. I'll write that in red to represent what's going on in our head. So we're not dealing with a 3 yet, we're going to be foiling. 2w times 2w is 4w squared. All this is going to be times 3. Outside terms are going to be 2w times 1, which is 2w. Inside terms would be 2w. The last terms would be 1. Now I can combine those like terms, 2w and 2w, which would be 4w. Plus 1 there. So you can see how that goes back up and it matches what we did here. So in red was checking, and that brought me back up here to the original trinomial. So I do have the correct factored version right here of 3 times 2w plus 1, 2w plus 1, and I can actually simplify that to show the exponent, and it would be 3 times 2w plus 1 squared because I have the same binomial being multiplied by itself. So that would be a perfect square trinomial shown there. 3 times the quantity 2w plus 1 squared.